Hey, welcome everybody to today's webinar on cavity-enhanced dual-cone spectroscopy with quantum cascade lasers. My name is Jakob Heiden. I am an application engineer at IOSweep, and I will be the host of today's webinar. I will be joined today by Markus of Caltech, USA. Hi, Charlie. Thanks for joining us today.
Yeah, good morning. Thanks for having me, or good afternoon.
Before handing over to Charlie, I will give a short introduction of about 10 minutes. Then Charlie will talk for 20 minutes. We'll give the main body of today's webinar about all the measurements we did, the setup and results. And in the end, there will be a questions and answers session. Please already during the presentation, use the Q&A button on the bottom of your screen to type in your questions. We will read them out in the end and try to answer them. So as usual, I would like to start with a brief introduction about quantum cascade laser, dual cone frequency spectroscopy. And starting from frequency cones, those are laser sources that do not emit at a single wavelength, but over a broad spectrum, all simultaneously at well-defined frequencies that are spaced equidistant along the frequency axis. And if we talk about quantum cascade laser frequency cones, we are looking at semiconductor laser sources that are direct current driven, so easy in operation, and they emit directly in the fingerprint IR region, where we have so much rich molecular and chemical information available. And in our spectrometers, we use two of these laser sources, and we overlap them on a beam splitter and send them together through a sample and onto a single point fast detector. So what happens at the detector is we will observe optical interference between the two laser fields, and this will result in sinusoidal signals on the detector, the so-called beat nodes, at the difference frequencies between the optical frequencies of the cones. And if you look at the spectra of these two cones, you see that the difference frequency will be different for each pair of cone modes. And therefore, we get a unique mapping from the optical spectrum to the radio frequency spectrum that we see if we take a Fourier transform of our time domain signal on the detector. And therefore, we need no interferometer, no other scanning type thing in our spectrometers. And this is why we can achieve the 1 microsecond time resolution with our instruments. These instruments are the Iris F1. On the one hand, this is our flagship spectrometer, the first turnkey dual cone spectrometer in the world with a 1 microsecond time resolution. In this work, we use the Iris core. This is a receiving bay for our exchangeable laser modules and coming also with drive electronics. Usually we ship this together with detection hardware and processing software that allows you to actually take dual cone spectra with this. The exchangeable laser modules that are used in both of those instruments typically cover about 60 inverse centimeters, somewhere in the range between 2,200 inverse centimeters and 900 inverse centimeters. Worth mentioning for, in particular, this application is the high optical power that you get from out of these modules of typically between 20 milliwatts and 200 milliwatts. Even 1 watt output power was demonstrated from a frequency cone. Now we're very proud of our most recent release, the Iris C. This is a more compact and also lower cost dual cone spectrometer. So the same technology, but in a more compact footprint. The default time resolution of this instrument is 1 millisecond, but also 1 microsecond is available. You see here in the picture with my colleague, those laser modules have been shrunk down quite a bit, still exchangeable, and they also come at a lower cost. Now, after this rather general introduction, I would like to set the stage a bit for the cavity-enhanced work by talking a little bit about gas phase spectroscopy with dual cone spectroscopy. And if you talk about gas phase spectroscopy, we care about two particular parameters. This is on the one hand, the spectral sampling, and on the other hand, the spectral resolution. Now, if I talk about spectral sampling, what I mean is the gap between data points on our frequency axis that we have in our spectra. And in our case, this is given by the repetition frequency of our lasers, which is about 0.3 inverse centimeters. The resolution, on the other hand, is defined as the smallest width of a spectral feature that we can observe in our spectrum. And this is limited by the width of the individual comb modes, of the individual lines, which is about 10 to minus 4 inverse centimeters. So we're looking at a situation where we have very well-defined frequencies, but a gap in between them where we are essentially blind. And this is a situation that works very well for larger molecules at atmospheric pressure, and you will see examples for this later. But for smaller molecules at lower pressure, where we have sharp and distinct absorption lines, we will miss a large number of lines. And this is why we would like to fill the gaps in between lines, which is achieved by spectral interleaving. So what we do here in this so-called steps technique is that we stepwise shift the center frequency of our combs. We measure again, we shift again, measure, shift, measure, and thereby fill the gap in between the two spectra. And this is an example of such a spectrum that was recorded in only 5 minutes and spans about 60 inverse centimeters with this very high time resolution. In this case, this is a low pressure methane sample. We can look more closely into this spectrum and analyze the peak positions of the absorption lines that we find in the spectrum and compare it to literature values to estimate the accuracy of our wave number axis. And this is what we did. In this case, we compared it to two different data sets. One is Hytron 2020, the gray data points, and the other one is a more recent paper, also a very accurate measurement based on frequency combs. And if we compare this, we see that the agreement is to within about 10 to the minus 4 inverse centimeters, just over 10 to the minus 4 inverse centimeters. We can also analyze the width of these features with the very well-known width. Because this is a low pressure sample, it is Doppler limited, so we know the theoretical width very well. And if we do that, we find that an agreement to within about 5 times 10 to the minus 5 inverse centimeters. Now, we could also show that you can combine this very high spectral resolution with the microsecond time resolution of our spectrometers. And there is a webinar on that given by Karin Kepler, and I warmly invite you to have a look at that. There's also a webinar, of course, on that, on step sweep by Muriel Lepere. So we have clearly the spectral resolution, we have the time resolution. So what about the sensitivity? And if we talk about sensitivity, what we want to maximize are two things. Probably the absorption cross-section. So we want to target the strongest lines, and I think that's a check because we target the fundamental for vibrational transitions in the infrared. And the other thing we want to increase is the optical path length. And the go-to thing here is usually multipath cells, like the circular multipath cells of IRSweep, the ISLS, which come in two versions, the 4-meter path lengths and 50-meter path lengths with exceptionally low sample volumes of only 30 and 130 millimeters. And this is kind of already a step towards cavities, because if we look at these cells more closely, what we see is that they are made up along the rim of spherical mirror segments, and these form a stable optical resonator. And for this reason, because it's a stable optical design, alignment to the cell is particularly easy. The angle tolerance is large, also the tolerance with respect to the beam, whether it's collimated or focused. So it is really a straightforward instrument. Now, 15-meter path length is, of course, quite nice, but there's some people for which even the longest path lengths will never be enough. And so introducing Charlie Markus. Charlie received his bachelor actually not only in chemistry, but also in mathematics. He did his PhD then under supervision of Professor Benjamin McCall, where he worked on subdoppler spectroscopy of astronomically relevant molecular ions, where he used cavity-enhanced velocity modulation spectroscopy for that. Then he spent some time in Germany with Professor Stefan Schlemmer. He performed their high-resolution mid-IR spectroscopy of ions and studied their reaction dynamics. And currently, he's a Beckman postdoctoral fellow at Caltech with Professor Michio Okumura and Dr. Stan Sander. He currently studies trace radical species using very sensitive infrared spectroscopic techniques and carbon growth through resonance stabilized radicals and fundamental H reactions. And with that, I would like to hand over to you, Charlie. So please share your screen and take over.
All right. Thank you for that kind introduction. Could you stop sharing so I can start sharing?
I sure can.
Okay. Oh, I got it. All right.
Well,
let me make sure this looks correct.
I can see your screen. Yes.
Great. And you see the slide? All right. Well, thank you for that introduction. And thank you, IRIS-Sweep, for having me here today to give this webinar. I'm really excited to share with you the results that we got on this feasibility demonstration, trying to do cavity-enhanced dual comb spectroscopy in the mid-infrared using this IRIS-Sweep dual comb instrument. But first, a little background on our group and the work I've been doing. So my research and the research of the groups at the Okamura lab, as well as at the Jet Propulsion Laboratory, are interested in the photochemistry of planetary atmospheres, where a lot of interesting chemistry is happening. So for example, here we have an image of Saturn's moon Titan, which is a cold environment, mostly nitrogen with some methane and hydrogen. And you'd expect at these temperatures, it would be pretty much inert. But what you see when you observe it is this opaque orange cloud of hydrocarbons and extended haze. And what's generating this rich chemistry is photolysis from sunlight. So UV light can photolyze methane, generating hydrocarbon radicals, which then proceed to grow in complexity to larger molecules, finally reaching, for example, the bottleneck to benzene, and then growing into larger polycyclic aromatic hydrocarbons, which condense and form hazes. And so chemistry initiated by, so photochemistry leads to this chain radical chemistry, which leads to a growth in complexity and condensation in particulate matter. And if we come to Earth, although it's a very different type of chemistry, it's a similar idea. So here we have, for example, photolysis of ozone leads to reactive O singlet D atoms, which then generate OH radicals, which can then oxidize volatile organic compounds, leading to these sort of oxygenated radicals, which then can continue to grow, become less volatile, condense, and lead to secondary aerosol formation, which can have pretty profound impacts on our climate, health, and the chemistry of our planet. And so when trying to understand these really complex systems, so people put together these very large networks of chemical reactions and models, but it's really useful to be able to zoom in on a single reaction and be able to characterize it fully for different temperatures and pressures in order to, let's say, improve the predicting power of these models. And one tool that we have for this are pulse laser photolysis experiments. And so this is a way to generate controlled reactions and then study them in the laboratory. So a strategy that we've used and others have used is to generate radicals from an intense pulse from a UV laser. So for example, from an excimer laser. And then you can use a variety of different methods to probe the products and reactants as they evolve. And in the Okamura lab, we've used cavity ring down spectroscopy. So this is taking advantage of putting your reaction volume between two highly reflective mirrors, which increases your interaction length, allowing you to observe very, very weak signals. Reason being is that when you generate these radicals, they have concentrations on the order of 10 to the 11 or 12 to 10 to the 14 per centimeter cubed. So fairly low concentrations, and they only exist from 100 microseconds to tens of milliseconds, but on relatively short timescales. And so in order to observe these species as they form and react away, you need something that is both sensitive and fairly fast. So here's an example of measuring the hydroxymethyl peroxy radical, in which you can observe its formation rate and under different, for example, initial radical conditions. And so this has worked well, especially for these sort of small, simple molecules, but problems start to arise when you try to go to more, let's say, complex systems. So there's this challenge, which is that chemical mechanistic complexity grows very rapidly with small increases in, let's say, the functionalization of a molecule. So here we have the potential energy surface of OH plus propane, which there's really only two paths it can take. And And now if we increase this simply to OH plus propene, now we have many different branching pathways, the option to both add and abstract from the molecule. And so now this is starting to become an intractable problem if you're really just measuring at a single wavelength or only measuring one molecule. And so this is what brought our attention, our interest towards using optical frequency combs, which combine these wonderful properties of being both broadband and a coherent source. And so you get the benefits of, for example, a CW laser while getting the coverage of 100 or more wave numbers. And they're a very natural fit for using enhancement cavities. And that's because, as Jakob said earlier, comb modes are separated at this very regular interval, and so are cavity modes to an extent. And so if you set the repetition rate of your frequency comb to match the free spectral range of your cavity or an integer multiple, then you can have very high coupling efficiencies or get all of your laser light, much of your laser light through, and still cover a broad range. And as was also noted, is that there's a lot of interest in bringing these techniques to the mid-infrared. And this is where strong fundamental bands exist for pretty much for most molecules that are infrared active. And if we just look at this spectrum of ethane, you can see in the overtone and combination band region, you can hardly see it on this scale, whereas these fundamental bands are quite clear. And so there's a lot of benefits to go here, in spite of the fact that the technology is less developed than in the near infrared. And so at Caltech, we've been developing techniques using interband cascade lasers, which frequency combs, which cover roughly 50 wave numbers somewhere in the CH stretching region. So here's an example of looking at the formation of formaldehyde. But we were interested in trying this with quantum cascade optical frequency combs, which is a more mature technology and has more power available and covers this fingerprint region. And so this is what kind of initiated this feasibility test. And so there's a lot of advantages for trying to do, for example, a dual comb measurement using one of these QCL comb dual comb systems, in that you have a very large amount of power per comb tooth. So we're talking milliwatts, which is huge for a frequency comb experiment, which also then grants you a large local oscillator power. So the comb that's reading out also has a lot of power, meaning that your signal scales with that. And so you can make very sensitive, measurements. And also the large repetition rate has the benefit of very fast readout times, which is good, for example, with kinetics experiments, when you are now being able to read out on this microsecond time scale, as well as it gives you some benefits in having higher sensitivity in your multi-heterodyne signal. But there are, of course, going to be challenges, which is that just an unfortunate reality is that high reflectivity mirrors just aren't as good in the mid-infrared. They have more losses due to scattering and absorption, meaning that your total transmission is going to be much smaller than, for example, mirrors in the near infrared. These QCL sources have issues with optical feedback, which when you're designing a laser, you usually are sending it at a mirror, which is sending it straight back. So that's an issue. And these systems are free running, and so their line widths are somewhat large, relatively large, on the order of 200 kilohertz. And so this can give you challenges as far as coupling to an optical resonator. But our objective was to demonstrate that this was feasible in this 9.4 micron region where this iris core unit that we were using covered. And so the way that we set this up, so here's a image of our optical layout. So we took the signal comb, we sent it through some mode matching optics and injected it into a bow tie cavity. And so the reason why that we used a bow tie geometry was that then light that isn't coupled into the cavity is reflected off at an angle instead of straight back. So this largely eliminated issues that we had with optical feedback, which was mostly just coming off of, for example, lenses. But we were able to just dump all the light that wasn't going into the cavity. The resonator had 114 centimeter round trip path length, with one of the mirrors on a translation stage to do rough adjustments to the length, and one mirror mounted on a piezo, which allowed for us to sweep the cavity length in order to ramp through the different cavity resonances. And the reason why we had to have this rough adjustment is that we wanted to set the free spectral range of the cavity to match an integer multiple of the repetition rate. And so when we found this condition of FRR equal to 28 times the FSR, we saw just in the DC transmission, these comb modes stack up, and many of them appear to transmit at the same time. And so at this point, if we were to just, for example, slightly detune, these would fan out into the comb spectrum, which would be similar to what vernier measurements are. But in our case, we wanted to try to do dual comb measurements on this transmitted light. And so with the local oscillator comb, we first generated a reference multi-heterodyne signal by combining a fraction of the signal comb with the LO comb. And then we also took the LO comb and overlapped it with the light that was transmitted from the cavity, collinearized them, and focused them onto a fast detector. And so after our first little tease of a heterodyne signal from our detection, after a heroic effort from Dan and Jakob in our short feasibility test, we kept this heterodyne signal kept growing and growing until we had a full comb coming through our cavity. And so here's what it looked like in the time domain as we swept the cavity length. And as you can see, there's this center burst in the middle. And if we zoom in, we can see that it's composed of these interferograms transmitting in sequence. And if we zoom in even further, you can see these interferograms, and they're separated by 400 nanoseconds, which is 1 over delta FREP. So it shows how quickly that we are obtaining these comb measurements over time. And so what we do with this is we bin them into 4 microsecond groups, and we performed a Fourier transform. And what the data ends up looking like is this in this heat map. So this is the absolute value of the transmitted heterodyne signal. So on the x-axis, we have the comb mode, and on the y-axis, as we move up, we're moving forward in time. And so you can see at early times, we have this group of comb teeth which are transmitting at roughly the same time. And then as we go forward in time, as the dispersion of the cavity mirrors cause a slight disagreement between the repetition rate and the free spectral range, the comb modes start to transmit sequentially, which is what you see happening here. But being a heterodyne detection, we have both a real and imaginary component of the signal. So here, if we just look at the real part, we get this candy cane-like structure, which if we look at different cross sections in time for these different comb modes, we see that the phase is rotating as we're going through these different cavity transmission signals, which is just due to the different path lengths from the reference and LO comb to the respective detectors. So we wanted to understand these transmission signals, and so we wanted to put together an analytical model of light that's coming through the cavity. So if we consider the electric field as it is passing through, so it's the sum of different amounts of round trips through the cavity. So from a single pass, we'll pass through 2 mirrors and reflect off 2 mirrors, t squared and r squared, and travel from mirror 1 to mirror 4. And then if we go 1 trip around, we have that plus 4 more reflections and traveling the length of the cavity, so on and so forth. And this is a geometric series. And so from this, we can get this nice analytical form of the transmission of a bow tie cavity, which has some subtle differences from example of linear cavity. And from this, we can calculate our heterodyne signals, which is going to be a combination of the real and imaginary components of this transmission coefficient. And here we can see we're looking at the transmission of 1 comb tooth. On the x-axis, we have our mirror detuning, and you can see that simply using the mirror parameters of the mirror reflectivity and the detection angle, we can very accurately model these transmission line shapes. And from knowing the detection angle, we can rotate this to 0 degrees, in which case we see the real part looks like this nice transmission signal, and the imaginary part is the dispersion of the cavity. And so from this, we can characterize our cavity at every single comb tooth. And so from this, we can determine R throughout the spectrum. So here we can see a plot of this with mirror reflectivity of about 99.75%, which is in fairly good agreement with the manufacturer's simulation. It's always a bit worse. We're not sure why there's this sudden drop off at low frequencies, but overall it's in good agreement. So this grants a finesse of around 310 to 680, which increases your effective path length by a factor of f over pi. So this means that we have an effective path length of between 114 and 250 meters, depending on where you are in the spectrum, which is quite good considering the size of our little benchtop setup as shown here. The finesse also gives us our cavity mode width, which is on the order of 400 to 800 kilohertz, which is larger than the mode width of our laser, which is estimated to be about 220 kilohertz. And so from this, this also tells us that it is appropriate to use the line width of these transmission features to determine the reflectivity of the mirror, as well as the fact that we have good mutual coherence between the comb and the cavity. And so next we wanted to actually measure a molecule, the spectrum of a molecule. So we chose methanol, which has this nice new 8 CO stretching mode within the coverage of the laser. And so what we did was, so as we're sweeping this cavity, just placed a drop for our first measurement near the cavity and let it evaporate into the volume. And so what we saw after a very short time scale was a substantial drop in the transmission. So here is the cavity transmission at each comb tooth, and what you see is this Q branch appear and an R branch, but the absorption was quite large. So here you can see we're dropping down to 20% cavity emission. And so this is well beyond the small absorption approximation. So we can't just treat this as an f over pi times L path length enhancement, but we actually have to analytically determine the transmission based on the absorption. So using the equation I had earlier and plugging in losses due to absorption, we can calculate in comparison to an empty cavity what we would expect our absorption to be. And knowing the cross-sectional contour of methanol, we can fit this spectrum and determine a concentration. So in this case, we measured a concentration of 1.7 times 10 to the 14. And I should say this is from a single acquisition. So this is only one sweep of the piezo and one frequency comb measurement. And so over time, so as the droplet evaporated over the next few seconds, we saw, well, initially we saw no methanol, and then a jump in the concentration, and then it diffused away from the cavity volume. But we also wanted to do this a bit more quantitatively. And so we had this purge box already built with the idea of trying to keep water out of the cell. But it proved to be a little bit too leaky to try to do methanol measurements. And so we did our best to patch it up with tape we had in the lab, and then flowed a steady stream of a dilute methanol concentration into the box, and then compared measurements of an empty cell to a cell with, or to an empty cavity with methanol. And here we were able to do a sequence of 10 averages. This was largely just limited by the length of time we had to do the measurement. This was on the last night that we were getting this done. But here we can see an average of 10 measurements, and we can start to see the rotational contour, the contour of the rotational structure start to appear within the R branch of this measurement. And so we can also convert this to absorption instead of just looking at cavity transmission, which removes distortions due to the change in finesse over the spectrum, as well as the fact that in the large absorption limit, you distort strong features. And so finally, we wanted to characterize the noise of the system by taking repeated measurements and seeing how the averaging behaved. And so here we consider the time on resonance to be our measurement time scale. And so over the course of 70 acquisitions in a row, we can consider that to be roughly 5 milliseconds of measurement time. So here we have the transmission of one comb tooth over time. And then we can take the Allen deviation, which tells us how the noise decreases over longer and longer measurement times, or averaging times. And here we can see this dashed line shows a root end dependent, so a white noise behavior. We can see that over the total length of our measurement, it was still behaving as white noise. So we were still benefiting from averaging. And we can do this for every single comb tooth. So here they are shown in this faded blue. And the average value for the noise equivalent absorption, so scaling that noise to the effective path length, we get an NEA of 2.7 times 10 to the minus 8 per centimeter per root hertz. And if we scale this by the square root of the number of comb modes, which takes into account the multiplexed advantage of a frequency comb measurement, we get a value of 1.85 times 10 to the minus 9 per centimeter per root hertz per spectral element. And so just to get an idea of what kind of sensitivities this would give us for a measurement, so given the cross-section of methanol, with our 2.5 milliseconds of acquisition time, we would have a signal to noise ratio of 1 for 2 times 10 to the 11 per centimeter cubed of methanol, so down to around 11 parts per billion. And for a, let's say, weaker carrier like benzene, we can get down to 1 times 10 to the 12 per centimeter cubed. But this does demonstrate that even with this first demonstration, which was done rather quickly, we are getting down to the concentrations we would need to do, for example, kinetics measurements, where we're measuring transient species that are on these same orders of concentration of 10 to the 13, 10 to the 14. But as far as future directions with this technique, there's a lot of very straightforward ways of further improving it. So for example, the optimizing the cavity geometry, making it a shorter cavity, which would have widen your cavity modes, allowing for better mutual coherence between the comb and the cavity, improving your sensitivity, as well as, for example, applying a dither lock. So if you were to keep much of your comb on resonance at all times using, let's say, a loose dither lock, you would greatly increase the duty cycle of your measurement. Instead of just getting one sweep through resonance every time you take a measurement, you'd be constantly measuring. So that would give you the full time resolution of your measurement, as well as much faster averaging times. And in this measurement, we didn't really have the full amount of time to perfectly mode match the cavity transmission with the local oscillator comb, which would also increase your multi-heterodyne signal. As far as what we'd be interested in using this for, so next would be to interface it to a photolysis flow cell, where even this module covers many interesting radicals, free radical species, such as the resonance stabilized radical ALL, methoxy radical, HO2, and nitrate. So there's a lot of interesting chemistry that could be investigated with a system like this. But in conclusion, this was, to our knowledge, the first demonstration of cavity-enhanced dual-comb spectroscopy in the mid-infrared. We accomplished using this IRIS sweep iris core system at 9.4 microns, covering 60 to 70 wave numbers in this 1060 wave number region. Our setup provided a path length of about 200 meters on our benchtop setup, and this entire experiment was completely free running. So there's no locking to the cavity, no locking the combs to each other. And so this makes it quite a robust measurement without having to deal with a number of servo loops that a lot of frequency combs experiments can have to contend with. So this technique could also be very conducive to, let's say, field measurements. And we demonstrated, and as a demonstration, we did trace measurements of methanol to show that we are able to measure trace species. So I would like to thank all the people who put in a lot of hard work over a very short amount of time to make this happen. So at IR Sweep, everyone who's involved, especially Jakob and Dan, who went really above and beyond. Jakob came jet lagged, and we put him to work pretty much immediately. Dan stayed an extra day to make sure that we got the final measurements done. At Caltech, Philip Cottrell, who was a rotating student with us, who maybe got a little bit more than he bargained for. We also had him working long hours, and then everyone in the group, including especially Terme and Doug, who also helped out with the measurements. And then for funding, I'd like to thank the Arnold and Mabel Beckman Foundation for support through their A.O. Beckman postdoctoral fellowship. And I would like to thank all of you for your time, and I'm happy to answer any questions you have.
Great. Many thanks. Thanks for this great presentation. There are indeed several questions, so I'll jump right in. The first question was somewhat could be expected. Are there any prospects for continuous rather than swept cavity QCL locking schemes. So
right. So I touched as far as locking to the cavity instead of sweeping through the cavity.
Right.
Yeah. So that was something that we were even hoping to try during that week. It was just a matter of time. So people in these experiments will do, for example, a loose dither lock, and that means you don't have as much of an issue with dispersion from the mirrors. So you can still, over a short time, couple all of your comb light through. And so in that case, yeah, we would get the full time resolution with the measurement. So we would hope to be able to do that.
With not off-the-shelf mirrors, but maybe some that are somewhat better suited to the center wavelengths that we have. All right. There's a question, are there plans to extend the wavelength range to around 3 microns, where one could access fundamental CH vibrations? Unfortunately, this is outside the region where QCLs can emit currently. So currently, fortunately, no plans to move in these directions. Yeah, so you kind of answered the question a little bit, but maybe you could elaborate a bit. How could you adjust this to follow microsecond time, microsecond kinetics?
Right.
Because I think what we observed was rather steady state.
Right. And so for measurements like this, so we've done in the past cavity ring down, where you're really only probing at one time point after the chemistry is initiated, and you just scan the delay time of your excimer to your measurement. And so this is possible when you're doing repeated measurements of the same event. So in this case, we would just scan the delay time of our excimer, and that way you would build up measurement times at every single point. And that's what we've done, for example, with the ICL vernier comb measurements. And so yeah, it would still be possible to, and in that case, your time resolution is just limited by the step size of your photolysis event. So it is possible. It is of course ideal to be able to measure with in a full duty cycle, but you can still get to the same time resolution.
Great. The next question. Methanol concentration in the atmosphere is about 1 ppb. Do you think it's possible to increase the sensitivity to reach that level?
Yeah, I mean, if you think that this measurement was only a few milliseconds of on resonance time, so if you were to be able to even just average longer with the same setup, or again, lock to the cavity, it would take a factor of, so if we're down to like 20, so a factor of 20 squared more measurement time, but our measurement time was fairly short in this example. So you could also, for example, go to a longer cavity to extend the length too.
Okay. There's a difference. There's a question. What is the difference between the local oscillator and the signal comb? Maybe I can answer that. In this case, they are both basically the same lasers. You could use both of them usually. The signal comb is a signal comb because it goes through the sample. The local oscillator bypasses the sample and is only after the sample, in this case, mixed or overlapped with the signal, so with the other comb, and creates heterodyne. And since it's bypassing the cavity, the power of the local oscillator is much higher than the signal comb, so we can actually amplify the signals, this heterodyne amplification that you get by this means of detection of the fairly low signal that is transmitted through the cavity. This question: what is the frequency resolution that you could obtain? So I did mention the frequency resolution of the individual comb modes, which we observed. It's a difficult measurement to do, but the indications that we have is that there's no systematic broadening, at least over the broadening of methane lines and other lines that you would expect from a N2O. So it's somewhere on the order of 5 × 10⁻⁵ was the scattering around the expected values that we saw. It's our best guess. I don't know if this could be, do you think the frequency resolution from the cavity itself could be higher than that? Basically, difficult probably, right?
Oh, sorry, what was the question?
I mean, this is probably the limiting factor, the frequency of the resolution of the comb rather than the cavity. In principle, you could, I guess, lock the cavity to something with a very high precision. Then maybe you can exploit that. Does work enough no longer. While we answer the other questions, would you mind showing the experimental schematic again?
Yeah, let me go back. Sure.
This is an interesting. Is the cavity mode size wavelength dependent? If it is, how is the mode matching done for all compounds? Is there a spectral element to that?
As best as you can. It will change with the wavelength of light, but over this range, the wavelength doesn't change drastically from 1030 to 1090 wave numbers. And so, yeah, we didn't have any issues with the mode that we were matching to, or the mode changing over the spectrum. If you mean in the spatial mode.
Yeah. Spatial mode, I think, is the question here, yes. Maybe the one thing to add there is that the quantum cascade lasers do emit single spatial mode, all frequencies, so that definitely helps. Yes. Coming back to the resolution, maybe I should, because it's a kind of question that, again, maybe I should add, in principle, we could combine this with step sweeping. Basically, you could, but a disalog, for example, could follow, I suppose, the frequency steps of your comb. In this case, you could also fill the gaps. In this case, it's a somewhat more complex experiment, probably, but I think it could be done. Then you can achieve the resolution and the sampling that I mentioned in my introduction. Let's try. We're somewhat slightly over the time, so try to pull in. There are more questions. Then I'll try to answer them, but let's pull in one or two more.
Right. So for Martin's question, so in this case, we didn't interleave. So our resolution, while our point spacing was set by the repetition rate of 7.4 gigahertz. But methanol was in this at atmospheric pressure, room temperature is a continuum. So we wouldn't really have benefited from, well, we could have interleaved to completely fill in the contour, but there weren't resolved lines that we were missing, for example. Yeah, so I guess quickly, one more question came in. So for some kinetics applications, a conventional linear cavity would be more useful, right, for as far as how to interface it. So the problem would be you need to have a proper optical isolator to prevent, it would be optical feedback is the challenge of going to a linear cavity, which is possible. Of course, you lose some of your light with that. And also in the mid-infrared, they're just less available and expensive. So, but with an isolator, an appropriate isolator, you can use linear cavities.
Yeah. Or if you had good mirrors with high transmission through the cavity, then also ND filters, probably you could even use ND filters to throw away basically a factor of 100 on the way in, a factor of 100 back, then they have an isolation of 10 to the 4. Maybe this could be also longer. There's a comment that one could use a V-shaped cavity. Unfortunately not. Same is true for a Brewster cavity. Or maybe, I mean, this is actually would be an interesting test. In those two cavity configurations, you still get optical feedback. You get it only on resonance. It's the opposite direction as an infrared Perot, right? Sorry for answering this.
So you might actually get mode polling to narrow your line width of your laser, but
might work. But
you could also go to a ring cavity geometry, so just a 3-mirror cavity. Again, bow tie was sort of set by the stock optics that we were able to get to do this measurement.
Yeah, and we just didn't dare to try the additional complexity of positive optical feedback and controlling the phase of the optical feedback in the time frame of a week. So I suppose that's the reason why we didn't try that. Okay, for the other questions, maybe we can try to follow up with these persons in directly. So thanks again for everyone who joined today, and have a good evening, and don't hesitate to reach out to us. Goodbye. Thanks, Charlie, for joining.
Yeah, thank you so much.